Okay, don't forget, we have a review session this evening, and it's long haul 207, it's 7 o'clock. Hopefully everybody will be able to be there. But here is sort of the trailer teaser of the review session right now. Let me have it. What you got? Yes, sir.
I got some questions that I took pictures of on my phone if you want to read them.
What are the questions from?
Textbook.
Okay. Or you can tell me what it is, because by the textbook.
Oh, yeah. Okay, so this one is review. Yeah, it might be a problem, but I just took a picture of the question.
Okay. So here's the question that is made. Post P. Suppose you have a linear transformation from Rn to Rm. Suppose B1, B2, B3 are linearly dependent. Suppose they're a linearly dependent set. Explain why why is this set also linearly dependent? So, question is, any ideas? How we tackle such an animal? Well, what does it mean to be linearly dependent in the first place, right? I mean, we can't do anything unless we know what it means. Yes, ma'am.
What is the factors in
Okay, so what does it mean for these three animals to be linearly dependent? Since B1, B2, B3 are linearly dependent, we can find numbers, say real numbers, A1, A2, A3, such that A1, B1 plus A2, B2 plus A3, B3 is equal to the zero vector, and I've left out an important factoid. What's one thing that we need to be able to say about A1, A2, and A3? They're not all zero. Maybe one of them zero, maybe two, but they're not all zero. So at least one of these animals is not zero, correct? Okay, so good. What we've done is we've captured what it means to be linearly dependent, right? There's a non-trivial linear combination of that that's equal to zero vector. Right? Now, how does that help us move forward with the problem? Yeah.
Well, I was thinking, so if you take the transform of A to AB, it's A times the transform of B.
Okay, good idea. So what you're saying, correct me if I'm wrong, but you're just saying, take this equation here and hit it with T, right? Smack it with T and see what happens, right? So let's do that. So just basically plug both sides of this equation into the same function, right? Now, what is, look at the right side of that, what is t of 0? Right, any linear transformation takes a zero vector, right? So here we have this. And this is a linear transformation, which means that I can break it up into pieces and pull out constants, right? Now, y'all holler at me, it just goes too fast, but because I took a couple of steps here. Right. But not all of these are 0, right? Well, we put it this way, at least one of A1, A2, A3 is not 0. So that means that these three vectors here are linearly dependent. Okay with that? By the way, could you say the same thing about this problem if you replace linearly dependent with linearly independent? That is to say, suppose V1, V2, and V3 were linearly independent. Is it true necessarily that TB1, TB2, and TB3 are also linearly independent?
That's the zeros.
Okay, that's right. Okay, let me give you, sometimes stupid examples are the best way to go. Here's my stupid example. Take the linear transformation 0 that takes every vector to the 0 vector. That's a linear transformation, right? So even in that case, if V1, V2, and V3 are linearly independent, if this is the 0 transformation, this turns all three of these into 0, right? And 0, any set that contains a 0 vector is never a linearly independent set. Anybody know a condition on T that will guarantee that, suppose this is a linearly independent set? Can you give me a condition on the linear transformation T that guarantees that these are also linearly independent? Well, you would want T to be 0, but you need it to be a little bit more specific than that. Can anybody think of one condition? If it's 1-to-1, that is correct. So see if you can show that. Suppose you start off with a linearly dependent, if you start out with a linearly independent set, and suppose T is 1-to-1, see if you can show that these are also, that the new set is also linearly independent. Any questions on it? Everybody understand what we did here? Okay, what else you got? Okay, yes.
Can you give an example of the subspace stuff with numbers?
So, what do you mean numbers?
Like, not like theory with this, but like numbers.
Okay, I'll make some notes.
Yeah.
I'll find. You know, find the null space of this, right? That's kind of such a big problem. Because remember, what is, by the way, what's the null space of subspace of? Well, so this is, let me give you a help there. This is a 3x4 matrix. I agree with that. 3 rows by 4 columns. What does it mean to be in the null space of this? Right, the null space is any solution to this homogeneous problem, or if you think about multiplying vectors, it's any vector that when you multiply by this matrix, you can 0, right? And so what size of a vector is it legal to multiply that by? 4 by 1, everybody agree? So the null space is actually a subspace of R4. By the way, if I ask what the column space is, what's that subspace of? Well, how tall are the columns? They're 3 high, so it's a subspace of R3, right? So the column space, subspace of R3, the null space, subspace of R. Everybody, okay, does this so far? Well, let's figure this out. How do we figure out the null space? Well, this is an old-fashioned reduction kind of, right? So that's what I'm going to do. And it's probably going to be ugly, but do it anyway. 1, 3, 1, 4. I'm good here. I'm out. And I'm going to multiply this by -3 and add. By -3 and add. By -3 and add. -3 and add. Now, I guess maybe the best thing to do is, I'll go ahead and do this and make it easier in the long run. 0, 1, 1 and a half. 0 minus 13, 4, maybe. Right. And now I'm going to use this one here. You know what? And I'm going to eliminate above and below. So I'm going to leave the second row same as it was. I'm going to multiply by -3 and add up here to come kill this. That's going to be -2. When I multiply it by -3, that's -3 halves plus 8 halves. And I am going to multiply by 13 and add to the bottom. See, that's going to be 17. And that's going to be 13 halves minus 20 halves is minus 7. And so, by the way, I haven't done it yet, but can somebody tell me at this point, I've got kind of a clear view here. What is what's the dimension of the null space? You know? Yes,
1.
it is 1. How did you know that?
As
Right. How many? Can everybody? How many pivots do I have here? Well, I've got them, but this is going to be another pivot, even though I haven't worked it out yet, right? So this is another pivot right here. So there's going to be 3 pivots, 1 free, and that 1 free corresponds to that free parameter. So it should be 1-dimensional null space. Right? Okay. So, I'll go through this. 1, 0, -2, 5 halves. 0, 1, 1, 1 half. 0, 0, 1. Minus 7, 34. And so if I wanted to get a basis of this, and we'll see, because we did say that the null space is going to be 1-dimensional. Let's actually see that in action here. I'm gonna use this pivot right here to nuke everything above it. And so this is going to be 0, 1, 0, so minus 1 and add. So this is gonna be 1/2 plus 7/34. So that's gonna be 24/34, 4, 12, 17. If you like. I'm gonna multiply this by 2 and add. So this is going to be, times 2 and add, we'll move that. That's going to be minus 7/17 and 5/2. So, well, I should do it on 34, I guess. So this is going to be minus 14 34, and that's going to be 85. So that's going to be 71/34. Everyone's favorite number. And now I've got to roll the dash line. So the solution to this homogeneous equation notice this turned out the way we predicted, right? Basic, and the x4 is 3, right? So my solution should look like this. X1, X2, X3, X4. Well, let's see. We have the equations here. An X4 of 3 in this instance. And the first line of that matrix gives me X1 plus whatever that forward fraction was, 71/34 X4, 0. Then I get X2 plus 12/17. X4 is 0. And finally, I get X3 minus 7/34. X4 equals 0. Notice how X1, X2, and X3 are all determined by X4, right? So I can rewrite this as X1 is minus 71/34. X4, X2 is minus 12/17. X4, X3 is 7/34. X4, and X4 is just X4. That's our free one. Minus 71/34, minus 12/17, 7/34. So my null space has dimension 1. X4 is like a free parameter, and that single basis element, that crazy stack there, minus 71/34 is all the way down to 1. That's my basis vector. Yes.
So if let's say you took this matrix A that you had the first 3x4, and let's say that was a transformation matrix, that would not be 1-to-1, right? Because that has too many columns.
That's a good observation. Yes, it would not be 1-to-1, right? Because this vector right here goes to 0, and 0 goes to 0 as well. So you've got more than one thing going to 0. Right? So it's not 1-to-1. Because remember, what it means to be 1-to-1 is any two different inputs have to be 2 different outputs, right? But if you put in that vertical stack there and multiply it by the matrix A, you get 0. And if you take the 0 vector and multiply it by that, you get 0. And in fact, if you take 2 times this vector, or 3 times this vector, or 100 times, you always get 0. So it's not 1. Good observation. Yes, Jake.
Say you were asking about column space, how would you solve that differently?
Okay. Let us make a bold prediction before we go off into column space world, right? So what do we have the dimension of the null space is? 1, right? Anybody tell me what the dimension of the column space is without looking before we even go off? It should be 3. That's right. Where'd you get that?
Well, there's one.
Right, we have the rank nullity theorem, right? Because the dimension of the null space plus the dimension of the column space should add up to the number of columns, right? We got that many columns, we have that for the null space, so the column space has to be three-dimensional, right? Okay. Everybody cool so far? All right, so suppose that we find, and I'm not gonna erase some of this because actually my computations here are gonna help me. Let's find column space, okay, or a basis for it. And our prediction is it should be three-dimensional, so let's cross our fingers for that. So we start off here, and I'm not gonna do any more work than I have to do here. So I quit. In fact, I quit after this. To blazes about these stupid fractions, right? How many pivot columns do I have? Right? I've got three. Everybody pick them out here. 1, 2, 3. In fact, I didn't even need to do that much work to know that there's three pivot columns. And that's it. So can anybody tell me for our basis for column A? Gotta be a little careful with this. What should it be? First three columns, what? Good. You gotta be a little careful with the column space because the row operations can change. It doesn't affect the linear dependence, but what it does affect is the span. So here, at this point, I've determined that those three things that I've circled in yellow are the pivot columns, correct? But don't use them. You've got to go back to the original matrix and use the corresponding columns. So basis for column A here would be just these things, which are 103, 3, 2, minus 4. And 1, 2, 7. These three vectors are linearly independent and they span column space. By the way, can somebody give me a different basis for the column space now that you know this information? By the way, the column space is contained in what? The null space is in R4. What's the column space contained in? Everybody agree? And in fact, the column space in this case is all of R3. Everybody agree with that? Because any two bases have the same size, right? So for this particular example, another basis for the column space could be 1, 0, 0, 0, 1, 0, and 0, 0, 1, because it works out that way for us here. Any questions? So this is a rather, my favorite basis for R3 is E1, E2, E3, 1, 0, 0, 0, 0, 0, 0, 1. But this is a basis too. Right? Why would you ever use such a messy basis? Well, there are circumstances where it might be easier depending on what your problem is. So, and we'll discuss that kind of thing when we get to like orthogonal and normal basis. Okay, any questions on that? Is that the kind of thing you would? Yes, I believe you had other questions. Didn't
Well, I raised my hand, but I put it down.
you retract the question? Okay, other questions? Yes.
From one of the past exams, fall 2025.
Okay, I can look that up real quick. So this is, what was it, fall? Okay, so let me, and this is from the exam,
Yeah,
number,
5 and 6.
okay, I'll just do this, I'll just do these here. This is, so the problem that we will currently consider And this one's not an easy problem, actually. So. This comes 5. Oh. 1, 1. That B. B. That. And lambda a scalar. This is just kind of, so here's what this means. V is a vector and lambda is just some number. It's just some real number. We say that lambda V is an eigenvalue eigenvector pair for the n by n matrix A if A be lambda. So. This is A is an n by n matrix. If A, B, suppose that P is an n by n invertible matrix. So here's what the problem is. Suppose that P is invertible. Suppose P is an n by n invertible matrix. Show that lambda V is an eigenvector pair for A. If and only if lambda inverse V is an eigenvalue. Sure. I'm sure I got it right here. Show that lambda V is an eigenvalue. Even though it's lambda the inverse V is an eigenvalue. Okay. Questions?
What are those words mean?
What's that?
What are those meaning? I don't understand.
Here's the great thing about math. Right? It does, because the definition of eigenvalue eigenvector pair just means that it satisfies this equation.
Oh,
A times B equals lambda V. That's it, right? And so how many of you, this intimidates you, this problem, right? Me too a little bit, right? Don't let the words fool you, right? Just take it step by step, this little piece, right? All it means to be an eigenvalue eigenvector pair is matrix times B is the same thing as lambda times B. And actually, if you want to get a little bit more warm and cozy with it, let me give you an example. Suppose A is and let B equal to vector XY. What happens when I multiply? The this minus one. What happens? Well, should be right here. What goes in the top? What goes in the bottom? This is 2 times x. So see what's happened here? A times b is 2 times b. So here my lambda is 2. So basically what this means is matrix. What this equation, again, the voices, but this is telling me that the matrix times b just stretches the vector. But it doesn't matter, right? All you gotta do is, okay, let's go through this. I don't think this is nearly as intimidating as it seems to be. Words. So let's see, what do we got to do? Show lambda b is an eigenvector for A, if and only if this thing is an eigenvalue eigenvector for P. Well, this was more intimidating. So let me write this down. What does this mean? What does it mean for just write down what the definition tells you. This is the pair, right? And this is the matrix. This is now playing the role of the matrix A. Everybody agree with that? So P inverse AP. Let's see, there's the matrix, there's the lambda. And what's my V here? What's playing the role of V? It's like acting. What actor is playing the role of V here in the definition? In this case, it's right. It's this. So let's suppose this is true. We need to show that lambda v is an eigenvalue eigenvector pair for A. Well, does anybody see something obvious that I can do with this side of the equation here? What happens to P inverse? That's right, they can't, it turns into the identity, right? So let me see, if I massage this a little bit, I get P inverse A B equals lambda P inverse B. Everybody okay with that? And remember where we're going. We need to show that lambda v is an eigenvalue eigenvector, right? So we need to somehow get this equation here. AB equals lambda v. Anybody see how we might do that? Okay, let me do one more little massage step here. I can move constants inside of matrices. And what are you just dying to do here? Anything jump to mind? Multiply by B. Good, good, good. And so this is now going to give P times P inverse is the identity. So that's times AB. And P times P inverse is the identity. And that's and there we go. We started here, got there, we're good to go. That's not so bad. There's a lot of words in this, which makes it intimidating, right? Like, look at this. P is an n by n invertible matrix. Why are those words there? Because the lawyers made me put them there. For me to be able to multiply this matrix times this matrix, it has to be n by n. For it to be invertible, right? Remember, there's all these inverses here, right? I have to put those words. They're necessary. And that's kind of it. Everybody okay? Now, all you got to do is drive your truck in reverse. And I gave you a hint for the other direction. Now suppose you start with we have to massage this and end up with so we started here and ended up here. We've got to also show that if we start here, we can end up here, right? So that you can drive the same in reverse. Well, I think all I have to do is kind of look at what I did before and sort of run it in reverse, right? So let's start here. AB equals lambda B, and let me kind of cheat back here. Let me kind of, let's see, where did I come from here? So I guess what I can do is I can multiply both sides by P inverse. I can multiply by P inverse because again, the words tell me that P's inverted. So there is such a thing as P inverse. And now, so now what I want to do is I want to get PP inverse here. And so really all I got to do here is all I did to go from here to here is I slid that PP inverse in there, right? No problem there because that's the identity. And this gives me exactly what I want because now I have P inverse AP. That's my matrix. Here's my vector. P inverse B is equal to lambda. And there. Any questions? Let me give you all some advice. On the exam, I am going to ask you some questions that are like definitions or simple computations, short things. And then I'm going to ask you some like this that you have to do. Well, you've seen the old exam where you have to do some maybe a little bit more involved computation. Here's a couple things. Number one, I tend to be nicer on the exams than on the homework because I'm very sympathetic to the fact that you all have an hour to do this, right? So even if you don't know how to finish a problem, draw me a roadmap. Oh gosh, I forgot whatever, but this is my general strategy kind of thing. I will award partial credit nicely. So just make sure that you tell me something that's relevant to the course about kind of what's going on. Number two, these problems all came up in honors calculus, or not honors calculus, an honors. So I like to push you all hard, but just before you're too intimidated, this is an honors section. Yes.
Do we have to go forward and backwards?
Technically, yes, because the problem said if and only if. Right. So here's what if and only if means. If I have a Lexus, then I have a car, correct? If I have a car, do I have a Lexus? And if you don't believe that, go look at that Roland McDonald stuff that I drive, right? It doesn't work both ways, right? So what you're showing here is it does work both ways. Okay. Other questions? Yes.
Can you do a span problem,
I'm sorry,
a span problem?
okay. Okay, I've got one, maybe. Oh, by the way, before I start the big example, let me throw this at you. Okay, so nobody has complained about a starting attendance or this thing, big extra. However, if you just one more day, complain at the 7:50 too early. I wanted to give you guys an hour, and I want you to have it uploaded by like 9 o'clock, probably 2 minutes after the exam. So, if there's any protest of that, just email me. I'm not gonna out you and throw you under the bus in front of everybody. Anybody's got a problem with that, so. Okay, you want a spam problem? Let me get my following matrix. Question, do the. The columns they span all over. How would we tackle such a problem? Well, what you're really doing is you're checking if the homogeneous equation. I hesitate to do that because actually your approach will work here because it's a square matrix, but I don't want to deceive too much. Yes.
I would reduce it and see if there's.
Okay, so you want to reduce, row reduce. It. When you row reduce it, what are you looking for?
If you're looking to see if there's been.
Okay. Okay, so it's something like columns and rows. So let's reduce this. So I'll reduce this using row operations. I like that row with the ones in it. So I'm going to multiply this by -7 and add. That should be plus this. So add minus 28, 3 is plus 25. Minus 23 and add. So that's going to be that's 46 minus 4 is 15. That's going to be 92, actually negative 92, and 17 is 75. Thanks. And look at it, lucky bugger I am, right? What's lucky about me? Oh, many things, that's right. No, well, in particular, what?
The third row is.
Right. The third row is multiple. Second, so I'll do one more, because then I think we can pass judgment. So does it span all part three?
No.
It does not span. all three. What do I need for this to span all of, in this case, all three? I need there to be a pivot in every. Yes, you actually need to span R3, you need a pivot in every row. There's one, there's no pivot down here, so it doesn't span apart. And actually, another way that you can do this, the first way that we looked at this kind of problem is another way, an alternate approach, which actually at the end of the day turns out to sort of be the same approach. Is this. You can set up the augmented. Matrix. Set three. Span all of R three, you have to be able to put any, you have to give a solution to anything that can appear over here, right? So the best I can do is write A, B, C, and then do my magic and see if I get a consistent, what I'm looking for is consistency, right? But I save myself the trouble because really I just work with this matrix and here what I have is a 0, 0, 0. And over the fourth bit behind the dotted bar, there would have to be anything in the world that you could ever dream of. And you can't get that for any. That's why you actually need a pivot and row for this case. Yes.
So if we had set the original matrix to 0 and solved for the vector, then that would just be the solution. Or I mean, that would just show that each column is in the span.
Well, so let me go through a couple of things. If you look at the column space, these are the two pivot columns, right? So the column space is actually, this is the basis for the column space, which is dimension 2. So what should the dimension of the null space be? 1, very good. So if you solve the homogeneous equation, if you went through and solved this, you'll get like, there's one free variable and you'll get a one-dimensional null space. Yes. Yes.
If we had solved that and like there wasn't a row of zeros and there wasn't a pivot in every column, would our answer just be yes, it does span all of our?
That's correct. If for this one, if you would actually have a pivot in every row, if you had a pivot in every row, then it would span our three instances. Yes. Yes.
This one's from the textbook. If the rank of a 7x6 matrix A is 4, what is the dimension of the solution space of A to X?
Okay, so let's on my race right. There it is. Okay, so if what did you have, a 7x6?
Yep, 7x6 matrix.
Okay, and the rank of this, what did they say? What was it? 4?
Yes.
Okay, so we've got a 7x6 matrix. The rank is 4. By the way, definitions. What is it? What does that mean? That statement? Yes,
Does that mean it has 4 linearly independent columns?
that is correct. Right. The rank of this, so there should be 4 linearly independent columns. Right. Continue. What's the question?
So it's asking for the solution space and I was gonna say, wouldn't it be 2 since those are the only 2 columns left there?
Read the question after it says rank is 4.
What is the dimension of the solution space of AX equals 0?
Okay. So this is just, I mean, what they're asking you for is the null space.
Yeah.
Right? And so the dimension of the null space of A plus the rank of A is equal to, this is important, it's equal to what?
6, right? It says total columns.
If I agree with them? Yes, because the dimension, it should be the total number of columns. What do we know? We know that the rank is 4, so M null A. That's right. So whatever this matrix is, when you solve for the homogeneous, you should have like, I guess, 2 free variables, and that'll be your basis. Or that those will be the parameters multiplied. Okay. Any questions? All right. Yes, sir.
the exam is lockdown browser.
Oh, thank you, thank you. Folks, bring your laptops or whatever it is that you use, your phones to upload it to, Canvas, right? But no, I just gonna sit here and stare at you very meanly, right? So we don't just lock down. I'll walk around. for this. Yes. Oh, yes, that's right. That's exactly right. The rank and the division of column space is the same thing.